This example actually is to apply the 8 rules that we learned about sketching the or drawing the root locus. So we are going to apply the rule one by one until we come out with the refining sketch of root locus or the final sketch of root locus. Such question is important actually, and you need to go or to apply the procedure step by step, one by one. So for example, you will be given the transfer function of the control system, either the the open loop transfer function of the control system here, which is GS, and you are going to use this GS actually in order to with the gain K. Okay, we are going to use it to draw the root locus. Root locus, we said it's generated due to the change of the value of the K in the closed loop transfer function. So in the case of open loop transfer function, the value of the K should be 0 in the characteristic equation here. So as you can see here in the denominator, there is no K. So the value of K for the characteristic equation here is equal to 0. But if we find the closed loop for this transfer function, that means we are going to find GS over 1 plus GS HS, even if HS equal to 1. Okay. So in this case, the value of the gain K will be involved in the characteristic equation. Thus, the changes in the K values will generate the root locus drawing or the root locus graph. Okay. So for this transfer function or for this open loop transfer function, the first we need to know is how many bulls and how many zeros do we have. And the number of bulls actually or number of zeros here depends on the degree or the highest order of the S here, the power of S. So as we can see here we have one S, and inside we have S square. That means we have, if we open this one, we will have the S cubed. So we have 3 bulls. If we have S square, we have 2 bulls. If we have S, we have only 1 bull. So we have 1 bull at the origin here, and we have 2 another bulls here from this polynomial. S square plus 2, 6S plus 25. Even this not easy to write it as a real bulls. We can calculate the bulls of this equation here, which is S25, by using the formula that we learned before, which is negative B plus minus 4AC over 2A. Okay, so the value of A here is equal to 1, the value of B is equal to 6, the value of C is equal to 25. Okay, so negative B, that means negative 6, plus minus B square, which will be 36, minus 4 AC, that means 4 times 1 times 25, so it will be 4 times 25, it will be 100 over 2A. A is equal to 1, so it will be 2. Okay, so the solution for this or the roots for this equation actually are S1 or S1 equal to negative 3 plus G4. The second one will be S2 equal to negative 3 negative J4. So in addition to the S3, or we can say S1 is equal to 0. So we have 3 roots or 3 bulls. S equal to 0, S equal to is a complex number which equal to negative 3 plus J4, S equal to negative 3 minus J4. So we have 3 bulls. We do not have any zeros here. The number of zeros or finished zero is equal to 0. So MB, number of bull, equal to 3, number of 0 equal to 0, number of zeros at infinity equal to 3, because we do not have 0 here, so we have all the zeros will be at infinity. Okay, so after we know the place of bull and 0, we are going to represent them on the S plane. So we draw the S plane, consists from the axis, which is sigma, the imaginary axis, which is j omega here. Then we represent the value of bull. So the first bull is as 0 here, so we just draw cross as 0. So this will be the first bull here as 0. Okay, the second bull will be at negative 3 plus J4. So this is negative 3 as a real number. This is plus J4 as the imaginary part. So the bull will be placed in this Q2 actually. This we call it Q2, this Q1, quarter 1, quarter 2, quarter 3, and quarter 4. Okay, so The second will be -3, -J4, so it's -3, and this is -J4. Actually, this is imaginary, so all the value here will be negative, positive J1, J2, J3, J4, J5, and so on. Here we have negative J1, negative J2, negative J3, negative J4. Okay, so this is the negative part of the imaginary axis, and this one is the positive part. So when we represent the poles, it will be identical or symmetry around the real axis. So we have one pole on the top, one pole here. Okay, after we draw the poles, do we have any zero? We do not have any zero. All the zeros will be at infinity. Since the zero will be at infinity, that means the root locus will start from the pole, go to the infinity, start from that pole, will go to the infinity, will start from that pole and go to the infinity. So we need to draw the asymptote. Since we have root locus will go to infinity, we need to draw the asymptote. So how many asymptote do we have? Number of asymptote here equal to MP, number of pole minus number of zeros. So we have 3 minus 0 equal to 3. So we will have 3 asymptotes. We need to find the angle of the 3 asymptotes, so that we need to find 2k plus 1 times pi over mb minus nz. Okay, so k equal to 0, k equal to 1, k equal to 2. So we are going to find the angle. After we find the angle of asymptote, we need to find the centroid point. So the centroid point actually, which is sigma here, equal to summation of pole, real part of the pole, real part of the pole of SP here, minus real part of the zeros over number of poles minus number of zeros. Okay, so we are going to see how to calculate the value of centroid. Then from the point of centroid, we are going to draw the asymptote lines, either like this one or that one, depends on what will be the angle of these asymptote lines. So as we can see here, from the angle of asymptote, we have the same angle here because we have 3 asymptotes. So the angle between them is 60. So it will be 60, 180, and -60. So we are going to have 3 asymptotes actually. What is the cross point of this asymptote with the real axis actually, or where they will cross the real axis? This depends on the value of centroid. I mean, how we can draw from this point, from that point, or we need to define what is the centroid point so we can start to draw our asymptote. So here we calculate the value of the centroid. So the centroid here equal to real value of pole minus real value of 0 over real value over number of pole minus number of 0. So if we just multiply here or substitute, so the real value of poles, if we have here 3 poles, we said we have 3 poles, correct? So we have 0, we have -3 plus J4, we have -3 minus J4. So the real value, that means we are going to highlight, or we are going to find the summation of these points only. The only the real value. Real value means 0 for the first one, -3 for the second one, -3 for the second one. So when we say summation of real part, it will be 0, 0, minus 3, minus 3. So it will be -6. Okay? Minus real part of 0. We do not have any finite number of 0, so it will be 0. Over number of zeros, number of poles, which is 3, minus number of 0, which is also 0. So it will be -6 over 3, so it will be -2. That means our centroid point will be at -2 here. The centroid point will be at -2. So from this point, we are going to draw 3 centroid, 3 asymptotes. One is with angle of 60, one with angle of -60, one with angle of 180. So this will be the asymptote lines. If we return here, we can see this is the asymptote lines. One with the angle of 60 here, one with the angle of -60. Other one is on the real axis, so its angle will be 180. Okay, so these are the 3 asymptotes. After we draw the 3 asymptote here and we draw the angle of asymptote, we find the centroid which is -2, we may highlight the part of the real. Actually, how many branches do we have here? We have 3 branches. Why? Because we have 3 pools. We have the first pool as 0, the second pool at -3 plus J4, -3 minus J4. So we have 3 pools. Number of pool equal to 3. So number of branches, which is the first rule, is equal to 3, is equal to the number of pools. So we are going to have 3 root locus, and this root locus, actually each one will start at the pool end at 0. Since we do not have 0 here, so it will go to infinity. Start at this pool and go to infinity with that asymptote. Start with this pool and go to infinity with that asymptote. Then we have the last one will start at this pool, which is the pool is 0, and go to infinity with the asymptote of 180. So this is how the general form of root locus will looks like. Okay. Always the pool, start at the pool, go to the 0. Start at the pool, go to the 0. Start at the pool and go to the zeros. All our zeros are at infinity. So infinity in this way, actually it will not interact. I mean, it will not cross this line. So it will go with in parallel to this line. Okay. So just to make it clear, it should be, I mean, this is just the general form of our root locus. So the root locus will be like this one. It has since it is a complex number, so it will start from the pool and go to infinity in parallel to the asymptote. It will not cross. It will never cross the asymptote point here. Okay, so it will be go in this direction. Okay, now do we have any 2 pools on the real axis? No, we only have 1 pool on real axis. Since we have 1 pool on the real axis, we do not have any breakaway points. We have only 1 pool point, because breakaway point you must have 2 pools on the real axis. Okay, do we have any 2 zeros on the real axis? We do not have any 0 on the real axis because our zeros all at infinity. So we do not have any 0 on real axis. So there is no 0 on real axis. That means we do not have any break-in point. So the rule number 6 is not applicable in this example. Why? Because the condition here is not satisfied. We do not have 2 pools. We do not have 2 zeros on the real axis. So we do not have real away point, real breakaway point and break-in point. Even if we try to calculate the breakaway and break-in point, we are going to find some number which is not applicable to our graph or to our sketch. Okay. So as we can see here, we assume that we don't know that we have breakaway or break-in point. We try to find if there is any breakaway and break-in point here. So we apply the differentiation method. We find the dk over ds for the function here. We derive this function. We make it equal to 0 as we did before. We solve this equation for s. We find the value of s here is equal to -12 plus minus -156 over 6. So it is a complex number. Since it is a complex number, that means no breakaway or break-in point. Just this step, you are not required to do it unless if you are sure that there is no breakaway at break-in point, no need to conduct this one. How to be sure? You need to check if you have 2 pools or 2 zeros on the real axis. Even if you have 1 0 here and 1 0 in the infinity, you may have break-in point here. If this point is 0, it's not a pool, you have a 0 here, so maybe you have a break-in point here, like this one. So it will be, since you have a 0 here and the other 0 at infinity. But we do not have any 0 here, so we only have one pool on the real axis. So if we double check here to do the calculation, we are not going to obtain any breakaway and break-in point. So here the number is complex. When it is complex, that means the number will be placed. If we calculate this one, negative 12 plus minus j set of 156. So for example, it will be placed in this area. So this, it is not a breakaway or break endpoint. If it is placed on this area, it's not breakaway and break endpoint. It must be located on the real axis. Okay. So this is regarding the breakaway and breakpoint, which is the rule number 6. Then if we go to the next rule, since we have a complex number here, I mean, we have complex pools. We have two complex pools. So these pools, they must have angle of departure because they are complex and they are a pool, so they have angle of departure. If they are zeros, they will have angle of arrival. Okay. So in order to find angle of departure here for this pool, we need to apply the formula that we mentioned before, which is the summation of pools angle of departure here. The angle will equal to 180 plus summation of angle of zeros minus summation of angle of pools. Or we can find the angle of the departure here is equal to summation of angle of 0 here, which is theta 2 for the, in the case, I mean, angle of 0 for theta 2, theta 3 minus angle of pole minus 2k plus 180. We are going to apply either this formula or that formula, same. So we are going to, in order to calculate the angle of departure for the complex number here, or I mean the complex pole. So in the case we already have our asymptote here, correct? So this asymptote, actually our transfer function will go, I mean our root locus will go out from, or departure from this line or from this pool and will go to infinity, and departure from this pool and go to infinity, and we can see it must be identical or symmetry with the other root locus. So how to find this angle? In order to find the angle, we need to draw a line from the existing poles to this pole. Then we apply the formula, which said the pole of S equal to negative 3J4 here. This is the point of the pole. So whatever is we draw a line here. So this is the angle between the pole and the angle of departure here will equal to 180 plus summation of angle of 0 summation minus summation of angle of the pole. We do not have any 0, so this part is not there. For the angle of the bull, since we have 3 bulls, so this already 1, so that the other we have only 2 bulls. So one bull is angle with, which is 90. Just erase this part. We can see here, if I want to find the departure angle at this bull, so we need to find the angle that the root locus departure from this area. So we need to find the angle between the axis here and, I mean, the horizontal axis with the departure of this part. Okay. So how to find? We need to draw a line from the other poles to this pole. Then we apply this formula, which is 180 plus summation of angle of 0 minus summation of angle of pole. So summation of angle of 0 is 0 because we do not have any zeros here. All zeros are at infinity, so it's ignored. Summation of angle of poles, we have this. If we say this is theta 1 here, this is theta 2. Here we already say theta. Okay, this theta 1. Okay, so the value of theta 1 here equal to 90. Okay, because this is perpendicular with the place here. So the angle here of theta 1 with the x-axis or with the horizontal axis is 90. The angle of theta here is equal to 180 minus this part. Okay, the 180 here, if we find this part, this is theta, this is 90 here, and here we have the angle of departure, which is the because it's due to the complex conjugation here, we need to find the angle of theta here, which is the angle of the third, I mean of this transfer function, I mean of this pool. So what is the angle of this pool here when we draw line? It will be the complement to 180. So what is the complement of 180 here? What is this theta? If we say this is theta 2, for example. So theta 2 here will equal to tan inverse opposite over this line, okay? Hypotenuse, okay? Opposite over hypotenuse. Or it will be cosine inverse this line over hypotenuse, okay? Or it will be tan inverse opposite over adjacent. So tan inverse opposite, which is the opposite here, this line is 4. The adjacent is 3. So it will be tan inverse 4 over 3. So I can find this angle. If I find this angle, I make 180 minus theta 2. It will give me the value of theta here. Okay? So the value of theta will be 180 minus theta 2. What is theta 2 here? Theta 2 is equal to tan inverse 4 over 3. Why 4 over 3? Because it's opposite over adjacent. Okay? Or cosine inverse adjacent over hypotenuse. It depends what's the value. So it's the easiest is to find tan inverse 4 over 3. So we can find the value of theta 2 here. From theta 2 we can find the value of theta. From theta here we substitute for theta in this equation, so we can find the angle of departure. Okay, so this is how to find the angle of departure. Angle of departure, if we want to find, we need to draw a line from the existing poles and zeros to the point of, or to the pole that we want to find the angle of departure for it. So our focus in this part to find the angle of departure for this pole here. So the angle of departure for this pole will be like this one. It will if the our root locus go there. Why? How I know it will go there? Because I already draw the centroid here, -2, and I draw the line for asymptote. It's not from my mind. I said it will go there. No, it depends on where is the place of asymptote. If the asymptote is there, so it will be like this one. If the asymptote is here, so it will be like 90 degrees. Okay, so it depends on the asymptote angle. So since we already find the asymptote angle, it is the centroid is at -2 and the angle is 60. So we should know already how it looks like. So it will go out from this point, go to infinity, go out from this point, go to infinity. And here we can see the symmetry between the two root locus. The third root locus actually is go from 0 to infinity directly, because it's follow the third asymptote, which angle is 100. Okay, this is how to find the angle here. So as you can see here, we calculate the angle of theta is 180 minus alpha. We call this one alpha. Okay, I call it theta 2, but it's alpha theta 2 any angle. Okay, then alpha is equal to tan inverse 4 over 3. So we find tan inverse 4 over 3, which is 126. Since one tan inverse 4 over 3, I don't 1 over tan inverse 4 over 3, it will be the complement of 126, which is 60 plus, maybe 63. Okay, so 63 plus 26, so it will be 180. Yeah, 53. Okay, so the angle here is 53 point something, 53.13 plus this one, so it will give you 180. So we find the value of theta, which is 120 degree. So this is the angle theta here, 120 degree. We apply, or we substitute for in the previous equation here for the value of theta. Here we put it 123 minus 90, 180. So this will be the result, which is -36. That means our or the departure angle for this board, and we said the angle always measure with respect to the horizontal line. So the angle here is which will be like this one, go from this way. The departure angle here will be -36. Okay, that means from this line here, the root locus will leave with angle of 36, -36 with respect to the horizontal line. The same here will be the second one will be leave also with -36, so it will be like this one. this is how to find the departure as his hair is more clear. Okay, so you can see here, this is the horizontal line, and this is the angle of departure, which is 36.87. Here is the departure line, and this will be the positive 36.8, because you can see here the symmetry. We can see here the centroid point. We can see here the angle is 60 and the angle of negative 60 and the angle of 180 for the third line. We can see three segments of the root locus, which is the bold here, bold lines. So this is one, this is two, this is three segments of root locus. Until now, we have the overview or the overall sketch of the root locus, but we still need to apply the last rule, which is the, one of the rule which is missing, which is the crossing with the imaginary axis. So we need to define this value here. For this one now, we, the overall, the sketch is there, but we need to add the crossing point with the imaginary axis, because this is very important to decide the system stability. So the system in this part will be unstable, in this part will be stable, and on this axis will be marginally stable. So how to find this point? We need to apply the rough table method. So we are going to write the characteristic equation. So this is the transfer function, actually our transfer function, and here is our characteristic equation, which is s cubic plus 6s squared plus 25s plus k equal to 0. We are going to draw or construct the rough table for, or rough array for this line. After we draw the rough array for this line, that means we are going to find s cubic, s squared, s, and s0. Okay, so S3 here, it will be 1, S1 it will be 25, S square will be 6, and this one will be K. Then here we have 25 times 6, 1 times K, it will be 1 minus K. It will be 26 minus times 25, 25 times 6 minus K. So we will have this rough table here. 6 times 25 minus k over 6, so it will give you 150k over 6, and here we have 2. So if the value of k, when k equal to 150, so this will become 0. So we have entire row of 0. If k equal to 150, this will be also 0. Okay, so we substitute here for k 150, and we write the equation for s squared, so it will be 6s squared plus 150. So 6s squared plus 150, or s squared equal to negative 25, s equal to root of negative 25, which will be plus minus j5. So from this equation, or from this solution, we can know what is the crossing point that we want to know here. It will be plus j5 and minus j5. Okay, and the value of the k here, which give you this crossing, the value of the k at this point and that point, k equal to 150, k equal to 150. Okay, if k equal to 150, the system will be marginally stable. From 0 to 150, less than 150, the system will be stable. K greater than 150, that means we are going to this area, so your system is unstable. So this is how we can define the stability of the system by using graph table. By using root locus. Okay, so by using root locus here, we can conclude, by using root locus, we can conclude or identify the condition for stability of our system. We said the value of k here will equal to 150, and the value of at this point, when the bool start or when the root locus start, k equal to 0. When the bool equal or when the root locus cross the imaginary part based on our solution in rough table here. We found k equal to 150. Okay, that means the bulls in this area, actually, whatever is the value of the bulls in this area, it will give us system stable. Okay, that means the gain for stability k greater than 0, less than 150. So this will give you the system stability or stable system. At k equal to 150, our system will be marginally stable because it's in the border of the stability here. If k greater than 150, so our system is unstable. Why? Because if k is more than 150, we are going to move on this part. So our bulls will be in this area. If the bulls are in this area, will be on the right half plane. This is right half plane. So if you have right half plane, that means your system is unstable. If the bulls on the left half plane here, so your system will be stable. This is how we can use the root locus to calculate the stability of the system. This will be the final sketch. So this is the cross point. This one the root number, I mean the rule number 8, which is the departure angle. We do not have arrival angle because we do not have zeros at the imaginary part here. Our zeros are at infinity. We have 3. If we just go through the 8 rules based on this graph or this sketch. So the first rule is the number of branch. So number of branch here or number of segment are 3. This 1, 2, 3. So 3 branches. The second one is about symmetry. We said root locus is symmetry around the real axis. So this is the real axis. We have a part here and the part is the same as here. So it is symmetry. Then the third rule is more about the real axis segment and the real axis branches or the real axis part. So on the real axis here, we have one segment which is on the left of the 0 bull here. We are on the left of one bull. So we have from 0 until negative infinity, we have one root locus segment here. So the rule 3 is applied. Then the rule 4, which is more on the centroid point. So our centroid point is calculated at -2. And all bulls will start, all segment of root locus will start at the bull. So we start here, we go to infinity. We start here, we go to infinity. We start here, we go to infinity. Why infinity? Because our zeros here, this is the first 0, for example. This is the second 0 here. This is the third 0 here at infinity or at infinity, at infinity, at infinity. Okay, so this is the rule number 4. Rule number 5, we draw asymptote and we find the angle for asymptote. So the first we define the 3 angle and we have 3 asymptote based on the number of bull minus number of 0. So we have 3 bulls, we have 0 0. So 3 minus 0, it will be 3. So we have 3 asymptote. The angle of asymptote are 60, -60. We draw, see, this is angle of 60 with the horizontal axis, -60 with the horizontal axis, 180 with the horizontal axis. These are the 5 rules. The 6th rule was about the real break-in and breakaway point. So we do not have any break-in or breakaway point here because we do not have 2 poles on the real axis, or we do not have 2 zeros on the real axis. So there is no breakaway and break-in point. The rule number 7 is more on the crossing with the imaginary axis. So we applied the rough table to find which is J5 and J -5. Actually, this is J because this is imaginary, because this part is J omega and this part is sigma, which is real, and this one is the imaginary. The rule number 8, which is more on the departure and arrival angle, we said there is no arrival angle here because we do not have zeros at the complex place. We do not have complex 0. We have complex poles. Since we have only complex pole, we have departure angle. So we use the formula to find the departure angle: 180 plus angle of zeros minus angle of poles. We draw line from the zeros and from the pole to this point that we want to find. Then we calculate the angle, which is 36.8 and a negative and 36.8 positive. So that's all. I mean, if you do like this one, you follow all the system. I mean, in the question of the final, maybe if you got such question and you apply the 8 rules, you are going to get the 20 points of this question. Otherwise, each step you are going to deduct some part of your